Hi, I'm Lindsay from StatsMedic, and in this lesson we're going to look at chi-square tests. This would actually be the first chi-squared lesson you'd learn in this unit. Over the next few lessons we're going to learn about 3 different types of chi-square test total. Today's lesson is about a chi-squared goodness of fit test. We have 2 learning targets. The first is to state appropriate hypotheses and then also to calculate the expected counts for a chi-square goodness of fit test. That's often abbreviated chi-squared GOF, so GOF is perfectly acceptable to use. Then we're going to calculate the chi-square test statistic, and you can see right here this notation. It looks like an italicized capital X squared. That stands for the chi-squared. And then also we need to find the degrees of freedom and the p-value that we'd use for a chi-squared GOF test. All right, so hopefully you have this page printed out. If not, you could just take notes in a notebook or on scrap paper. Just make sure you label everything correctly so when you go back to look over your notes, you can see which lesson it was from. So in this lesson today, we are talking about M&Ms. So Mars, that's the company that makes M&Ms, they claim the following distribution for the colors of M&Ms. So they say that 13% of M&Ms should be brown, 14% are yellow, 20% orange, 16% green, 24% blue, and 13% red. And what we're trying to figure out is this actually true? So what we're going to do is we're going to take a bunch of M&Ms and then sort them by color. So if you have some M&Ms at home, you could go ahead and do this. But otherwise, you can use this data here that I collected with my students. So we had a total of 461 M&Ms, and you can see here all the different colors and how many of each type that we had. So next what we're going to do is we need to think about our hypotheses. So when you think to other significance tests you've done, like a significance test for a mean or for a proportion, those are written symbolically. So we do like mu equals some value. Chi-square tests are actually different because while we could use some symbolic notation, generally it's actually easier to just write them in words. Because if you look at your the context here, if I have 13% brown, well that's P for proportion brown equals 0.13, but then I also have 14% yellow, so I'd have to have another equals 0.14, and so on, and then I'd end up having tons of different proportions that I want to describe. So instead what we're going to do is we're going to think about, okay, well we have this whole distribution, and this is called our claimed distribution. So since that's already given to us, we're not going to go ahead and list that all again. You could if you wanted, but it's also fine to just say the claimed distribution. So we're going to use that when we're writing our hypotheses. And what we're trying to decide with this question is we're trying to decide, is this claimed distribution true? So if we're trying to decide if something is true, with a significance test, we go ahead and we assume it is true. But then we try to see if we have evidence to the contrary. So what that means here is for our null hypothesis, we're going to say the claimed distribution of M&M color, so wanting to always get context in there. Oops. Claimed distribution of M&M color is true. And then the alternative is going to be the opposite. So the claimed distribution of M&M color is not true. So you can see how these are different from hypotheses that we've done in previous significance tests, because here we're just writing them in words and not really using that symbolic notation. Okay, so now let's think about where we need to go from here. Well, let's suppose that the M&M's claimed distribution is correct and that it actually is 13% brown, for example. Well, if that were true, how many browns would we have expected to get in our sample? I know how many browns we did get in our sample. We got 55. But what I want to know is how many should I have gotten? So pause the video and take a few minutes to try to calculate the expected values for our sample. So remember, we had a total of 461 M&Ms in our sample. So how many of them should be brown? How many of them should be yellow? Based on the distribution or the proportions that the company gave us. When you're done, go ahead and play the rest of the video. Okay, so let's look at your expected values and see if you got what I had. So I'm going to start with just brown. For brown, I got 59.93 brown M&M. So I want to talk about where that came from. So first of all, we were told that there should be 13% brown And now if our sample is 461, that means I need 13% of 461, which gives me this 59.93. Couple things here is, first of all, when you are finding your expected values, make sure you leave the decimals on. You don't want to round to whole numbers, even though we think of M&Ms as their discrete variables, or you're wanting a whole number. With this, an expected value is really like finding a mean. We call means expected values a lot. So this is saying how many browns did we expect to get. Now let's talk about what these values mean. So this first part here, this 13%, that came from the claimed distribution, and that's a proportion. So I'm going to use the variable P. And then this 461, that was our sample size, so I'm going to use the variable N. So what I did here was N times P, which is something you've probably heard many times this year. That is our large counts condition that we check. So N times P. Now remember also we have multiple values for P. We've got proportion brown, proportion yellow. So what I'm going to do here is I'm going to put P with a subscript of I, meaning you do this for every proportion that you've been given. So double check and make sure that your expected values are the same as the ones I have. And then now we're going to work through this table below to calculate our test statistic. So again, pause the video, and actually what I'd like you to do now is to work through the entire rest of this front page. When you're done with that, go ahead and push play and we'll talk through it. Okay, so you can see here now I filled in my whole table. I started with my observed values, which we got from our sample, put in the expected, and then just went ahead and did all the operations that you were told to do in the table. So I ended up with all these values over here, these ones, the observed minus expected squared divided by expected, and then we were told to add them all up, and that gave me about 25.69. Now, if you're off by a little bit, that's fine. It's probably just rounding error, but you should be reasonably close. And you'll notice here it says this is our test statistic. So prior to this, when we've done test statistics, we've had either Z or T test statistics. This is a new type of test statistic, and it is called a chi-squared test statistic. And a chi-squared test statistic is found by doing this observed minus expected squared. So I'm going to put that here. I usually just abbreviate. So observed minus expected squared over expected. But then we added it all up. So I'm going to do a summation notation there. So that is our formula for a chi-squared test statistic. You do your observed minus expected, square them, and then divide by the expected, and that gives you your chi-squared. Now, we're not asked to do it here, but let's think about how we would turn our test statistic into a p-value. So with a Z test statistic, we'd go to table A, or normal CDF. With a T test statistic, we go to table B, or TCDF. So Z is table A, T is table B, so chi-squared is table C. So let me pop up on the screen real quick a copy of table C. And you can see on table C that you need degrees of freedom. Now our degrees of freedom here are a little different than they were with our T distributions. Your degrees of freedom with chi-squared, I'm actually going to pop up here back to question number 3. In the margin here, what I'd like you to write, degrees of freedom, they actually equal your number of categories minus 1. So in this case, we had 1, 2, 3, 4, 5, 6 colors. So 6 minus 1 is 5, so we would have 5 degrees of freedom. So on table C, we'd go to row 5 for our degrees of freedom, and we move over until we find a chi-square test statistic that's close to 25.69. And for this one then, that actually takes us all the way to the end of the page. So our p-value here, let me add this in, p-value, we'd go to table C, degrees of freedom row 5, and then since it's actually off the page, we're going to write this as less than 0.0005. And I'll show you on the next page as well how you could do this with chi-square CDF in your calculator. All right, so let's talk through number 4 and 5. What value would you get for a test statistic or for a chi-square if our sample was very close to what's expected? Well, if it's really close to what's expected, our observed and our expected values would be very close. So when we subtract them, we'd get something close to 0. So in this case, the value should be close to 0. And if instead our sample was very far from what's expected, we'd expect a very large number. It's all relative, depends on how many degrees of freedom, things like that what does large value mean. But we're talking about the farther away from 0 you are, that means the sample was farther from expected. All right, so now let's go ahead to the next page and talk about our important ideas. So we mentioned before that there were 2 learning targets for today. The first one was about hypotheses and expected counts. So I'm going to put this here like this. Learning target number 1, I'm going to start with hypotheses. And these are hypotheses for a chi-squared goodness of fit test. So again, with chi-squared, it's mostly just hypotheses in words. And in this, I'm going to say the claimed distribution of, and then I'm going to put like a space for context. So the claimed distribution of, in this case, M&M color is true. And then the alternative is that the claimed distribution is not true. Okay, the next thing we had to figure out were our expected counts. And this is where we took each proportion and multiplied it by a sample size. So what I'm going to put here is, again, Pi times N, where P is the proportion or the probability of each category. And then N is our sample size. All right, and our next learning target was about finding the chi-square test statistic. So I'm going to use this capital X notation, and that is our chi-square. So chi-square test statistic. And we find that by taking the sum of all of the observed values minus the expected values squared divided by expected. And then from there we need our degrees of freedom, which were your number of categories minus 1. And then you can go to table C to find the p-value. As mentioned, you could also do this with chi-square CDF, which would be in the distributions menu on your calculator. In a chi-squared CDF, you're going to put in your lower bound, upper bound, and degrees of freedom. And then your lower bound in here generally is going to be your chi-square test statistic. It's possible it could be the upper bound depending on the question, but almost always it's lower bound is chi-squared, and then upper bound just put in some large number, and then your degrees of freedom. All right, so let's try a practice problem. Pause the video and then try this problem on your own. When you're done, go ahead and push play and we'll go over the answers. All right, so let's go over the answers. So in this context, Carrie made a 6-sided die and she wants to see if it is fair. So she rolled the dice 90 times and came up with these outcomes. So she got, for example, the number 2, it landed on 28 times out of 90 and so on. So we're going to start with our hypotheses. So in this case, we'd say the claimed distribution of 1/6 probability for each roll is true. It's because if it's a fair dice, it should land on each of the 6 outcomes pretty equally, meaning has about a 1/6 probability for each. And then the alternative is that the claimed distribution is not true. So in other words, the dice is not fair. To calculate the expected counts for each of these, since they're all equally likely, each of the 6 outcomes should occur about 15 times. And then to calculate the value of the chi-square test statistic. So with this one, you'll notice here, I didn't actually show every single calculation. So I started with this one, 12 minus 15 squared over 15. That is using for the first one here, outcome number 1. And then I showed number 2 as well, but then I just did a plus, ... plus. That's totally acceptable for showing your work. Generally, I like to show the first 2 calculations and then do a ... and then show the last calculation. But of course, I'm just entering all this in my calculator. One nice way to do chi-squared in your calculator is to type everything into your lists and then work off of those. But we get a chi-square of 14.4. For D, which degrees of freedom should you use? There are 6 categories. So we do 6 minus 1 and you get 5. So you're going to go to row 5 on your degrees of freedom on table C, and then move over until you find the chi-squared close to 14.4, and then look at the tail probability. And on this one, we get a tail probability or a p-value between 0.01 and 0.02. So for a conclusion, because that p-value is small or less than 0.05, we reject the null, and then we'd have convincing evidence that the dice is not fair. All right, so that's everything for day 1 of chi-square goodness of fit tests. And the next lesson, we're going to turn that into a full significance test by also checking conditions, making conclusions, that type of thing. So we'll be putting it into the full 4-step template of state, plan, do, conclude. And that's in the next video. So we'll see you then.